Hello everyone, welcome to this lecture. This is a continuation of the previous lecture on CVDs, and CVD, as you know, stands for chemical vapor deposition. So, in this lecture we will look at two different kind of CVD. One is called LPCVD, low pressure chemical vapor deposition, and PECVD, plasma enhanced chemical vapor deposition. So, let us start with the first one, which is low pressure chemical vapor deposition. So, as the name suggests, the LPCVD, in LPCVD we have to lower the total pressure of the gas stream, and lowering the total pressure of gas stream, what happens, the diffusion would increase, and if the diffusion increases, then the reaction control regime to higher temperature, the reaction control regime would also extends, right. So, if you read the first line, it says that lowering total pressure of the gas stream, increasing the diffusion and extends the reaction control regime to higher temperature. So, in this case, if you want to give a rate of deposition in LPCVD or in CVD process, the rate of deposition is given by R equals to, in the bracket, Hg Ks. So, Hg is mass transfer coefficient, then the reaction rate divided by mass transfer coefficient plus reaction rate into Ct by N into Y. So, the Hg and Ks, right, this in this, the Ks and Hg control the rate of deposition, whereas the overall process is governed by smaller of these two, correct. Mass transfer coefficient, now what is Hg, right, mass transfer coefficient. So, let us see the definition, is the ratio of diffusivity of the precursor and boundary layer thickness. The diffusivity of the precursor through the boundary layer is inversely proportional to total pressure, so number of collisions between the molecules. While in LPCVD, P total is increased from 1 atmosphere, which is 760 torr, to 1 torr, and so the diffusivity increases by 760 times, correct. So, we have said that the total pressure increases the diffusion, and you can see here the decreasing P total increasing delta S, but not proportionally. Roughly this change in pressure increases dg by 760 times and delta S by 3 to 10 times. The net effect of Hg is it increases almost 100 times. At lower pressure, Hg is higher, the system operation switches to surface control regime, and if that is the case, the temperature of operation of LPCVD is around 300 to 900 degrees centigrade. Since the system is operated in surface reaction control regime, temperature should be precisely controlled. So, this is very important statement, that if the temperature, if you say that we have LPCVD at 900, that means it should be within very small margin of error. Okay. So, you cannot have 900 instead of the temperature is 700, because everything is depend on the temperature, and it is the reaction occurs on the surface. Additionally, the advantage of low pressure system is faster diffusion through boundary layer to the main gas streams, and that is why it prevents auto doping. So, if you do not want to have auto doping, mostly you see LPCVD, the auto doping would not be there. Also, the shadowing may occur only if the flux of gas phase impede locally by surface topography. So, the effect of shadowing also will be less, but it is possible to have the effect of shadowing depending on the surface topography. As LPCVD is performed at higher temperature, the substrate as well as deposited film should be able to withstand that temperature. And this is very important statement, because if I have, let us say, take an example, if I have a silicon wafer, and if I want to grow silicon dioxide, deposit silicon dioxide using PECVD, using LPCVD, this is your SiO2, right, and this is silicon wafer. Then in this case, LPCVD can work very well, not a problem at all. But because why? Because if I have temperature of 900 degrees centigrade, right, silicon can easily withstand 900 degrees centigrade. But what if I have a silicon dioxide oxide layer, okay, on which I have, let us say, a micro heater, as we have taken example of micro heater, right, on which I want to deposit a silicon dioxide again using LPCVD. this is your SiO2, this is micro heater with nickel as a metal. Then this one is your SiO2, this one is silicon, this one is your SiO2, right. In this case what will happen? What will happen if I have nickel as a micro heater material and if I want to deposit SiO2 using LPCVD, what do you think what will happen? You see the temperature is extremely high. This nickel which is on which we need to deposit silicon dioxide, the nickel will not be able to withstand the temperature, and these are the cases where LPCVD fails, or the limitation of LPCVD is that it cannot be used where the substrate or the deposited film cannot withstand higher temperature. Okay. So, to overcome this we have another CVD called PECVD. We will see how PECVD works. Now, typically this reaction LPCVD uses silicon containing compounds, typically silane, SiH4, or 20 to 30% of silane is to 80 to 70%, 70 to 80% inert gas, which are reacted at the wafer at about 0.2 to 1 torr and about 575 to 650 degrees centigrade. So, in that case the question would be, where should I use LPCVD, isn't it? So, the LPCVD is used for 1, polysilicon for gate contacts, and polysilicon can be doped using diborane, arsine or phosphine. Doped polysilicon makes good short interconnect lines, right. So, in this case we can use LPCVD. Next is, if I want to have thick oxide isolation between metal interconnects, we can do that as well. What does it mean? So, suppose I have two metal pads, okay, and a metal bar, right, and then I want to make sure that this one is covered with silicon dioxide, then I can make sure that only this region is covered with thick silicon dioxide. If I want to do that, I can very easily do that. Okay. So, thick oxide used for isolation between metal interconnects. Doped oxide useful for global planarization. Doped oxide for global planarization, right. So, we can dope the oxide onto the silicon. Next one is, or you can use it also as a masking layer. For example, if I have silicon dioxide and if I pattern it, and then this silicon dioxide was grown and then patterned using photolithography and then I have boron which is diffused through silicon dioxide and silicon, right. Then boron will penetrate into silicon here, causing P plus, assuming that there is N type substrate, but boron would not be able to penetrate in this region because silicon dioxide is present. This silicon dioxide can work as a masking oxide, So, that is the second thing that we need to understand. Then we can also use for high K dielectric for larger capacitance, right. You do understand that there is a thin layer of oxide between gate and the channel, right. If you have source, if you have drain, here you have thin layer of oxide and then you have gate, isn't it. This gate is a conductive plate 1. This one can be a channel, if channel is formed, conductive plate 2, and there is oxide that is there, right. So, what happens? Two conducting plates separated by dielectric or air. What is that called? That is called capacitor, right. Two conducting plates separated by dielectric or air. So, this oxide that we have here generally we call is a thin layer of oxide grown using thermal oxidation, dry oxidation. But there are groups which work on high K dielectric materials, and if you have high K dielectric materials, then you know that the capacitance would be large. There is advantage of doing that. We will not go to that in because it is not part of this course, but you just keep in mind that if you want to have a better capacitance, higher capacitance, you can use high K dielectric material. Next one is silicon nitride is used for encapsulation, sealing up the circuit to prevent contamination from moisture, plastics used in packaging or air, etc. right. So, finally LPCVD consumes less amount of expensive gas compared to APCVD, right, we have seen earlier. Okay, great. So, let us go to the next one, which is the beautiful PECVD. Why I said that? Let us understand. Okay. So, plasma enhanced chemical vapor deposition is used widely as a deposition technique to deposit any material where there are reactions on the temperature the substrate can be exposed. For PECVD, an additional use of thermal source to provide energy for the chemical reaction, a plasma source is used. You have the similar things, you have 13.56 megahertz double cable power, there is a gas in, right, there is a top electrode, there is a bottom electrode with substrate, there is a heated table, there is a chamber, and then when you have a gas in presence of this two electrodes, what will happen? There is a creation of plasma, and then on the substrate in the presence of plasma, the reaction of the chemical happens to grow different films. The advantage of this is that, that the temperature is no greater than 350 degrees centigrade. The maximum is 350 degrees centigrade. You can also grow at deposit at 100 degrees centigrade. Okay, as low as 100, the maximum is 350. So, usually PECVD of dielectric is done at temperature of 200 to 350 degrees centigrade. By varying the temperature and flow of gas phase, PECVD allows us easy alteration of the deposited film, I mean changing composition, density and stress. The advantage, and why I said I like this system, is that you have a material which has a lower melting point, let us say about 500 degrees centigrade, right. This is silicon dioxide, extremely high melting point, we do not worry about it. This is also silicon dioxide, extremely high melting point, we never worried about it, right. SiO2, SiO2, and then we have silicon in between, that also has a very high temperature withstanding capacity, we do not worry about it. But what if I have here a nichrome or a nickel or a aluminum? Can I grow silicon dioxide on this, right? Can I grow a silicon dioxide on this? The answer is yes, we can when we go for PECVD. Why? Because the temperature is less than 100 or from 100 to 350 degrees centigrade. Even here it is 200. I have used PECVD at 100 degrees centigrade as well. Only point is that the rate of deposition will decrease as you decrease the temperature. Okay, but you can very well control the film thickness, you can change the flow of the gas, you can change the temperature, and with this changing of the parameters will change the overall composition of the film, the stress in the film and the density of the film. Okay. So, the advantage of PECVD is that you can deposit dielectric materials at lower temperature. This is used exclusively when we are going to fabricate MEMS based devices. I had I have brought a term called MEMS, right. It stands for micro electromechanical systems, micro electromechanical systems based devices. Okay, based devices. So, MEMS, when we used MEMS based chip, MEMS based sensors, MEMS based devices, everything uses or most of the time we will use PECVD, we will see. Okay. Now, to create high electric field is applied. So, what to create what? To create plasma, right. You can see here, just to have a representation, you have here purple color plasma, right, because when you see it looks like bluish purple color. So, to create plasma, high electric field is applied with a RF source of 13.56 megahertz to a low pressure chamber about 50 millitorr to 5 torr, generating ions and free electrons. In the plasma, interaction with the high energy electron causes the precursors to dissociate and ionize into various species and as ionized as well as excited molecules and neutral molecules. So, if that is the case, the thing will be that we can grow the different dielectric materials, and any material that can be reacted with the substrate surface of the substrate at different temperature. But generally exclusively we will see the use of PECVD in growing the or depositing silicon dioxide. So, incorporation of the byproducts into film is very common in PECVD. Incorporation of hydrogen, oxygen and nitrogen is common and can result in outgassing, peeling or cracking of the film during subsequent processing. Film density and stress depends on the condition of the deposition. So, this is a little bit of limitation of PECVD. However, standard PECVD is adequate for covering and filling structures with large dimensions, and this is beautiful, right. For smaller dimension, higher aspect ratio, other methods are more useful, one such as HD PECVD. But for the larger dimensions and you want to cover the fill the structures with larger dimensions, the PECVD is an advantageous technique. The limitations of PECVD are the use of hazardous gases and incorporation of byproducts or gas molecules in the film, right. That is the disadvantage of PECVD. So, now if you want to see PECVD at a glance, we can create high electric field applied between two electrodes in the presence of RF frequency 13.56 megahertz. There is a gas, inert gas, it goes in, there is a process gas which also goes in with inert gas, and then there is a heated plate, the byproducts comes out, the wafer is placed one wafer at a time. That is something that we are using with PECVD. The disadvantage of this particular process is that it may leave unwanted byproducts, it is a little bit costly, and stoichiometry is not really guaranteed, particularly when we talk about silicon nitride. It can be Si X and Y instead of Si 3 and 4, X and Y can be some numbers. Suppose you have a metal like this, titanium or gold or aluminum, you can deposit silicon dioxide on that because the temperature of this PECVD is lower. So, the advantage are lower temperature process, provides reasonable deposition rates, good film quality and conformal. Conformity is very important, particularly when we talk about structures which are flexible in nature. Okay. The silicon dioxide should be conformal with the structure of the substrate. This we will see particularly when we are talking about implantable devices for brain. Okay. So, we will talk about conformity in that particular case. So, now the point is, suppose after metal lines like aluminum was deposited, how would you deposit a conformal dielectric layer to isolate the next layer? You see here SiO2, Ti, and then SiO2 again you want to have a Ti. So, in that case you should, if I have Ti here and there is a Ti here, right, then this will be short circuit if SiO2 is not there. So, how to grow SiO2 over this kind of material where the temperature or melting point of this material is lower? So, we can use PECVD. When fast diffusing metals like copper are used, this lower temperature deposition becomes extremely important, right. So, this is the advantage of PECVD. Now, if you just let us glance HD PECVD, high density plasma chemical evaporation combines PECVD with bias sputtering to obtain good film of narrowing gaps. Very small gaps, if you want to fill it with the oxide layer, you can use HD PECVD. High density plasma can be generated using electron cyclotron resonance ECR and inductively coupled plasma. Okay. So, deposition is done at 150 degrees centigrade with a chamber pressure of 1 to 10 millitorr range. So, that is another thing that you need to keep in mind, that the deposition is done around 150 degrees centigrade. Second is that ion bombardment is enough to raise the temperature. So, no heating is required, instead often cooling is required to keep temperature less than 400 degrees centigrade, and relatively denser film can be obtained with the help of the HD PECVD. Okay. So, like I said, we are just glancing about it, we are not really going into detail about the physics, the chemistry of that, but to understand that there are some techniques, there are some tools that can be utilized to deposit films. Depending on the application, you can use deposition at a lower temperature or you can use deposition at a higher temperature, right. So, that is the point that I wanted to make in this particular class, but this is not where we have to finish. There is one more CVD that we need to look after, and that one is called the ALD. Okay, is a part of CVD ALD. At ALD will be the one that will be the last topic in the CVD section, and ALD stands for atomic layer deposition. Now, it is very important technique, particularly when you want to grow a ultra thin film of a material. Okay. So, what is ALD? Let us see that, and then let us see the CVD at a glance, okay, and then we will end the lecture. So, if you see the screen, ALD or atomic layer deposition is used for depositing ultra thin layer of material. This process can deposit single layer of metal at a time. As the precursors or precursors are not sent at the same time, the deposit process is well controlled. In brief, the substrate is exposed to first precursors, followed by purging away the excess amount, followed by application of second precursor and purge stages. So, it is keep on exposing, flushing out, exposing, flushing out, exposing, flushing out. That way you can have atom by atom layer of deposition, forming a layer using deposition, or what is we call ALD. So, atomic layer deposition is often performed at lower temperature, which is beneficial for working with thermally unstable precursors, and the advantage is that a wide range of materials can be deposited using ALD, including oxides, metal, sulfides, fluorides with wide range of properties depending on the application. You can see here is a source from Springer, right, where you have a chemical, it reacts with a substrate, and then there are atoms, it forms a layer, and then again there is a purging, and again there is a chemical. So, you can form this beautiful thin layer of film, ultra thin layer of film using the atomic layer deposition technique. So, the process consists of sequential pulses of gaseous precursors that react at the substrate surface. That is one thing. The first set of precursors are introduced into the chamber, adsorbed on the substrate and reacted with the substrate surface. Okay. So, we need to understand that how this process works. So, like I said, it is a sequential pulses of the gaseous precursors, and the first time the first set of precursors are introduced and then adsorbed the substrate, and then it is flushed, then second set of precursors are introduced. Okay. So, the individual gas surface reaction is called half reaction. During each half reaction, the precursors from container is pulsed for a set amount of time, and carried to the reaction chamber to allow the precursors to fully react with the substrate surface. Okay. So, though this is self limiting process, the coating will be highly precise down to monolayer, right. That is the advantage of this particular process, that we can have a monolayer of coating, atom by atom deposition of the material. Subsequently, the remaining gaseous precursors and reaction products are passed away from the chamber by a carrier gas. So, every half reaction cycle there is a formation of some layer and then next layer. This is then followed by another sequence of pulsing, as I told you, right, and purging of counter reactant precursors, creating one full layer of the desired material such as metal oxides, sulfides and nitrides. So, this one, then purge, then another one, then purge, another one, and you have a thin layer of the material. All right. So, that is what is shown in the previous slide as well, correct. So, this is the ALD process for you. So, as I told you that this process is then repeated until a desired film thickness is achieved. This we have seen in the previous slide, as you can see here. To know more about ALD, please visit the Springer article. It is given here, right. You type in Google, you will find the article. Okay. So, in summary, if I want to say what are the advantages and limitations of atomic layer deposition, the advantages are, as this is a chemical gas phase thin film deposition method based on sequential self saturating surface reactions, ALD is well controlled deposition technique that can deposit monolayer of 1 angstrom, as thin monolayer as 1 angstrom. Okay. So, that is one advantage. The second is most ALD process operate between 200 and 400 degree centigrade. So, the temperature is also extremely low. ALD process have been developed for a wide range of materials, including oxides, nitrides, carbides, fluorides, certain materials like 2,2,6 and 3,2,5 compounds. That is another thing, that several kind of materials we can deposit. But the major advantage of this technique is that the reactions are self limiting, meaning that at each step reaction proceeds until the surface, at reactive site is completely recovered with the precursors and then stops, and then we flush and then we introduce the another precursors. Like I said, is the half reaction steps, what you can say, or half reaction gas surface reaction, which is called half reaction cycle, right. And then the limitations of this techniques are the rate of deposition is slow because the deposition must be performed layer by layer, that is one thing, right. Rate of deposition in the range of 100 to 300 nanometer per hour. This is the little bit of limitation, because 100 to 300 nanometer per hour is an extremely low rate of deposition. Also there is one more thing that we need to take care, which is the surface contamination. The surface contamination results in surface defects in growing film which cannot be repaired. Okay. This is another thing we need to really understand, that the surface contamination will affect the film quality, properties of the film, right. So these are the limitations, advantage and limitation of the ALD technique. So if you want to now summarize why we cannot use CVD in common laboratories, right, why you cannot just have CVD installed everywhere, because many gases that are used in CVD are toxic, and particularly they are hazardous to humans, corrosive in nature, which will cause the corrosion to stainless steel other metals. They are flammable, burns when exposed to an ignition source, an oxygen source, either explosive and or pyrophoric, that means spontaneously burn or explode in air, moisture when exposed to oxygen. So what is the what we should do, right. The important point is safety, right. The safety and the proper control of the gas, proper control of the byproducts, right, making sure that the byproducts comes out and we do not just expose it directly to air. If it is a harmful, right, we need to process the byproducts. So all these things requires you to have a proper clean room setting, and then for each system you should have a proper engineer working with the system. So you cannot just use CVD everywhere. That is why even for the laboratory that we have, which is a clean room, we do not have CVD, but we have CVD as a process or as a technology available with our mother facility, which we call SENSE, right, in the institute. So the different gases, if you see, and the hazardous limits, the flammable limits and exposure limit, you can see that we use several gases like ammonia, silane, arsine, phosphine, hydrogen, nitrogen oxide, hydrogen chloride, diborane, dichlorosilane, and all these materials are either toxic or flammable or oxidizer or corrosive, right. So this is very important. Also you see the limits is so low, right, 16 to 25, it is pyrophoric, silane is pyrophoric, phosphine is pyrophoric, hydrogen 4 to 74. The exposure limit you see, just 25 ppm of ammonia is extremely harmful here, right, 0.5 ppm of silane, 0.05 ppm of phosphine, 0.3 ppm of hydrogen, 0.3 ppm of phosphine, 0.05 ppm of arsine, right, 0.01 ppm of diborane. So this is extremely low parts per million, alright. This is the exposure limit, and that is why it is very important that there is no leakage, right, and every few weeks one can see the health of the system. Okay. So in general, this is the last slide. What I wanted to show it to you through this slides or through this lecture is that we have deposition techniques, we have thermal evaporation technique, we have E-beam evaporation technique, we have sputtering technique. These are all three in physical vapor deposition. But when you can talk about chemical vapor deposition, these are ALD, CVDs, CVDs, PECVD, LPCVD, APCVD, right. And then the advantages of CVD is that it can have a better conformability, one. Second is that the shadowing effect will be less. Third is that the step coverage would be better. So these are the advantages. The limitation is that here the harmful gases are used, sometimes the rate of deposition extremely low, and then the flammable limit, the hazardous limit are there. The optimization is extremely important. Some CVDs are at really high temperature, but some CVDs are at low temperature. So when we fabricate a device, you should keep all this in mind, and you can mix and match the different technologies, different techniques to realize your device. Okay. So, we will see that in the coming lectures. One thing that I wanted to show it to you before we really move into the fabrication part or into the brain research part is micro machining. Okay. Something very important technique called micro machining. You know machining, right? You take a material and you machine it. You can either do subtractive manufacturing or you can do additive manufacturing. If you use 3D printing, you are adding layers onto the substrate, additive manufacturing. But if you have a metal and we want to create let us say a diaphragm in the metal, you are doing subtractive manufacturing. So, how additive manufacturing will be used, how subtractive manufacturing will be used. So, that all we will learn in the next class what we call as a micro machining. Okay. So, till then you take care. I will see you in the next class and we will learn quickly the surface and bulk micro machining, followed by what are the EEG signals, how the signals are originated, what are ECOG signals, and then how we can start fabricating device that can be implanted for applications like epilepsy, Parkinson. Also we will see a technique to understand the EEG arising from 1020 system and how the signature would vary depending on whether a person can hear or not. Okay. So, this all things are part of this entire course. I will see you in the next class with micro machining and the details of micro machining. Sometimes you may feel that the topics are little bit difficult to grasp, right. So, do understand that a CVD is a process of chemicals, right. So, require a good chemical engineering background, chemistry background to understand how the reaction occurs. Also there are a lot of physics, how the gas is introduced between two electrodes, how much the voltage we are applying, right, what frequency we are using, how this plasma will generate, right. So, you do not worry about all these things. My request to you would be that understand the technology that is there and try to utilize the technology to fabricate device. Okay. And that is what the focus is. If you want to go in deep physics, we will take another course for that, right. We want to understand reactions, there is another course for that. But to understand how the devices are fabricated, to understand how we can implant these devices into the brain, you to understand how the brain signals originates, to understand what are the applications of these devices for acquiring different signals in the brain. That is what our idea should be, right. So, that is where we are focusing on. So, let us meet in the next class and discuss more about micro machining. Till then, you have a great time. Cheers.